Welcome to this lecture series in linear algebra. We are starting a new module which will be about determinants, a central concept in linear algebra. And this lecture will be devoted to motivating the notion of the determinant. And we will see technical details also. So all we need to know is, well, strictly speaking, we don't even need to know about bilinear forms, but it will help. So if you know about bilinear forms, then this lecture will be a little bit easier to follow. Even if you don't know, doesn't matter. But yes, I do recommend that you do learn about bilinear forms if you want to understand linear algebra well. There is a separate module devoted to these in this lecture series anyway. All right. So the idea of the determinant map, as of now, we are not going to define the determinant or even talk about the determinant of a linear map or a matrix or anything. What we are going to do is define the determinant map or discuss the motivation behind it. And here is the motivation. Think R2, we have R2, and suppose we have two vectors in R2. So we draw them like this, but as we know, they are just points, right? Vectors are just points. And what you can do is, you can complete this parallelogram, right? And ask for the area of this parallelogram. In R2, there is a notion of area built into it. In high school, we talk about triangles and their areas and whatnot. So just borrow from that knowledge. One can talk about the area of this parallelogram. And if you remember from high school, the area of this parallelogram that you complete by, sliding this and that, whatever. So this parallelogram is that, but we will be interested in oriented area. What does that mean? We have this vector first and this vector second. So this kind of is trying to denote that orientation. You may have learned the right hand rule. You put your palm of your right hand in this direction and then curl your fingers towards this one, then the thumb will look like it's coming out of the paper. So that's positive orientation, and similarly you have negative orientation where you keep your fingers aligned with this and move them here. All right. So the signed area is this. So it's either positive or negative. So this is what we will be interested in. Okay. Similarly, we have a notion of volume in 3 dimensions. We had 3 vectors. And you can complete the parallelepiped now this time. It's no longer a parallelogram, it's parallelepiped. And the volume looks like this. There are absolute values here, but again, we will be interested in signed volume, and that will require a notion of orientation on R3, which you can't just talk about in terms of your fingers. But there is a notion of orientation, and you can talk about signed volumes. Okay, so the determinant assigns the notion of volume to an arbitrary vector space in some sense. You're given some vectors in an abstract vector space. Let's say it's an n-dimensional vector space and you're given n vectors, then the n-dimensional parallelepiped spanned by those vectors, whatever that means, we want to assign the notion of volume to it. In case of R2, we have our usual intuition that, or whatever usual mathematics that talks about area and volumes. I mean, area in R2 and volume in R3. But in an abstract vector space, there is no notion of even length. You can't talk about the length of a vector. In an inner product space, you can, right? If you have an inner product space, then you can take the inner product of the vector itself with it and take the square root. That you can call the length of a vector, but we do not want to work with inner product spaces. We don't want to restrict to inner product spaces. One reason for doing that is we want to have the notion of determinant to work for vector spaces over arbitrary fields. Inner products are defined only for real and complex vector spaces, but the notion of determinant should, or we want it to make sense for any vector space, finite dimensional for the moment. I mean, finite dimensional, not for the moment, but only for finite dimensional vector spaces. Okay, so we do not want to work with inner product spaces. That would be too restrictive for us. Right, so we want to assign an abstract notion of volume to an arbitrary finite dimensional vector space. In this sense, meaning given some n vectors, where n is the dimension of the vector space, we want to kind of assign volume to the parallelepiped spanned by them. So that is the motivation. And let's get into it. What should be the properties such a thing should satisfy? And to see that, first off, in this lecture, we will only discuss the two-dimensional case. In future lectures, we will discuss the general case. So, fix any arbitrary field, doesn't have to be real or complex. The determinant function, as we saw, is supposed to be a function which consumes two vectors from F2. So it consumes two vectors and it consumes them in an order. So this ordering is kind of what is taking care of the orientation. Which vector comes first matters. Okay, so it is a function from pairs of vectors to the field. Now, since we said that determinant is supposed to capture the volume, and when you're outputting your volume in an arbitrary field, that does not conform to intuition. So for the sake of intuition, think of f as the set of real numbers, but that intuition is motivating a very general definition, which may not make intuitive sense all the time, but it will also be it will at the same time be a very useful concept. So for the sake of intuition, think of f as R, but the definition that we'll give will be completely general. So a determinant function is a function from F2 cross F2 to F. Well, we are talking about only two-dimensional case, which is why there is a 2 here. Okay, so it consumes two vectors and produces a field element with the following properties. So it should be a bilinear function. Let me motivate why do we require this property. Suppose we want to assign the area to this pair u1v. So u1 is a vector in the vector space F2, and we have this pair u1 comma v. So the determinant is supposed to be answering what is this oriented or signed area. Similarly, u2 comma v, if you apply the determinant, it is supposed to answer what is this signed area, right? So if you make the vector u2 and make the parallelepiped, this area we have just translated it to make it here, right? But what would be the area of the parallelepiped spanned by u1 plus u2 and v? So this is u1, then we make u2 with the tail of u2 coinciding with the head of u1. So what will be the area or the signed area of this particular two choices of vectors? So it should be intuitively clear that it is nothing but the sum of this area and that area. But the first one is just the area of this parallelepiped and the second one is the area of this parallelepiped. So at the very least, we should, or it is reasonable to ask that the determinant function satisfy this axiom. Right? So this axiom is motivated immediately from our intuition in R2. Similarly, in the second coordinate, if you play the same game, you may demand or you should demand this. Right? And the same goes for scaling. So I leave it to you to justify this in this picture. So the intuitive meaning of this will be left to you. And these four axioms together just say exactly that the determinant function is a bilinear function, bilinear form on the vector space F2. So bilinearity is well motivated. Then we have this axiom that for any vector v in F2, we have the determinant of this pair is 0. And this is also intuitively clear. So you have some vector v. What is the area of the parallelepiped spanned by v and v? Well, the parallelepiped spanned by v and v is just this thin line. And a thin line has 0 area. So this is reasonable to demand. Okay, so this is an axiom that we put on the determinant function. And as a consequence of this axiom, very important to note, consequence is that determinant of this pair is same as minus determinant of the flipped pair. right? So what is the reason? Why should this happen? The reason is, just consider this thing. What is this thing? This thing is 0 because of this axiom. Instead of a v, substitute u plus v. So this is 0. And now invoke bilinearity. So by bilinearity, we will get right. This equality. This equality happens because of this axiom. So this is true, but the left side is 0. The first term is 0 because it is of this form, determinant of u comma u, so it's 0. And the last term is also 0. So I'll just erase everything. And this equation immediately tells us that this consequence is indeed true. So we need to just remember that. And lastly, normalization. Note that the constant function 0 satisfies the first two axioms. And that's a silly function. That is not a notion of area on anything. So we have a normalization axiom or a non-degeneracy axiom, which asks us, which says that the determinant of the two standard basis vectors taken in order is the identity of the field element. E1, E2, so E1 and E2 in picture. The determinant function assigns this the area 1. So in R2, this is very clear. In R2, this is E1, that is E2. And what is the parallelepiped spanned by E1 and E2? It is the unit square. And we are just saying that the area of the unit square is 1. So in R2, this is again well motivated, and we have just abstracted that out for any field. So that's the determinant function for two-dimensional. And any such function will be called a determinant function. Any function with these three properties will be called a determinant function. All right. But then the question arises, how many such functions are there? And you may have guessed the answer is only one. And that is the next theorem, if you will. We are saying that the determinant of this vector comma that vector is exactly what we saw in R2, the signed area. The same formula holds even for a general field. And this will be a consequence of the three axioms that we just wrote down. So let's quickly prove this, and that will be the end of this lecture. So we have the determinant of this pair of vectors. This is equal to, just changing notation, this is x1 e1 plus sorry, what have I done? This is x1 e1 plus, it looks a bit ugly, but what can I do? Then this is x2 e1 plus y2 e2, right? That's what it is. But if we invoke bilinearity, and for the moment only split out the second slot, we get x2 right. So the first slot is held fixed. This is held fixed, and the second slot has been made available to bilinearity to give us this. Now we will split out the first slot. That gives us plus right. So we have so far only made use of the bilinearity axiom, but now we use the second axiom. So this goes to 0 because the same vector appearing two times. So this is 0. And by the same reason, this is 0. And by the normalization axiom, this is 1. While by the consequence of the second axiom that we saw on the previous page, this thing is minus determinant e1, e2, which is minus 1. So this is a minus 1, right? So maybe I'll write that down here. This is equal to minus 1, and this is equal to 1. All right. So that gives us x2 minus y1 plus y2x1, which is what we claimed. This is x1 y2 minus x2 y1. That's it. So there is only one determinant function, right? And in fact, you can check that this is indeed a determinant function. So this satisfies all the three axioms. You can check that. And any determinant function must be same as this. So there is a unique determinant function on F2. And yeah, in the coming lectures, we will define the general notion of determinant for any Fn, and then we'll define the determinant of a matrix and that of a linear map. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.